Okay. Congratulations for making it at 9 o'clock after dinner the night before. And you've made it through almost 3 weeks of lectures. It's excellent. Um, so last time I told you the simplest theory, supergravity theory in 4 dimensions, n equal 1 4-dimensional supergravity. And as you could see, it was quite intricate. I want to kind of stress to you that it's kind of beautifully intricate the way it works, right? You have to introduce exactly these right connections, exactly the right terms, and the super works out. So that's a very, very non-trivial thing. And I was trying to give you a bit of an idea about how you might do it more geometrically. So we were talking about supermanifolds. Oh, should we go for? So we're talking about supermanifolds. And I'm just sketching some ideas for you. So the idea here is that we have now a manifold which has coordinates, so a point on the manifold is labeled by a bosonic coordinate and a kind of fermionic coordinate. And in this case, m is 0, 1, 2, 3 for the space-time dimensions. And mu is 1, 2, 3, 4. And these are going to end up being spinor directions, right? The moment we haven't got any spin groups, so there's no way of saying we've got spinors. And if I look at the tangent space at a given point, this is isomorphic to R, and we write it as 4/4, which means that it's a vector space. It means it's got 4 bosonic bits and 4 fermionic bits. And if I introduce a frame, so where I'm going is I'm doing G structures, but now I'm doing it on a supermanifold. If I introduce a frame, if I have another frame, it's generally going to be some general transformation of this frame, of the first frame, by some m. Sorry, how do I want to write this? Yep, some m b a of the original frame. And what kind of matrix is this? Well, it's a matrix which acts on this 8-component vector. So this M is kind of split into 4x4 blocks. And this block has to be bosonic, that block has to be fermionic, that block has to be fermionic, and that block has to be bosonic. So that these blocks take the fermionic coordinates and mix them into bosonic coordinates, or take the bosonic coordinates and mix them to fermionic coordinates. These blocks keep you in bosonic or fermionic. And this group here is the general linear group, but now with 4 bosonic and 4 fermionic directions. Okay. So what you might imagine is we now want to do some geometry. And you might think what you want to do is introduce a supermetric. So that would be something that allowed you to, so if I've got a vector here, which is a section of the tangent space to this manifold, I might want to have some supermetric which gives me the length of the vector squared as some gm n vm vn. That would be an obvious thing to do. So, but this is interesting. So if you think about this, this is going to, if I think of Vm as having my bosonic bits and some fermionic bits, then the norm of this thing squared is going to look something like, well, it could look something like the standard, you might choose sort of eta mn, vm, vn, and then here I'd have some other matrix. Let me call it omega mu nu, V mu, V nu, and this would have to be symmetric. But this would have to be anti-symmetric, right? Because these anti-commute. So whereas normally when we have a metric, so a conventional metric, would be invariant under SO or O31, say. This supermetric is actually invariant under a supergroup, which is called OSP314. So, yeah, there could be. There absolutely could be. So I just chose to write one down without the mixing. Yep. But what I want to stress to you, so this might be the standard metric, like the one that was Minkowski metric, right? And I could choose this omega to be just something that like 0, 1, minus 1, something like that. Say that would be some standard metric. So what I want to point out is that it's going to be this OSP, this is orthogonal symplectic. And the symplectic is because it's preserving this anti-symmetric thing on this bit rather than a symmetric thing. So there is a group you might think about. So if you had some supermetric in our language, that would be as a G structure. The supermetric is equivalent to OSP314 subgroup of GL44 as supergroups. But it turns out this is not what you do. This doesn't give you. Because what you might try and do there is do that, and then you would keep going, and you would then continue to super Levi-Civita connection and curvature. And so on, right? That might be one way you think of going. That would be the natural way to go, maybe. That doesn't give you supergravity. That doesn't give you the theory one. Well, it gives you a theory. I mean, you can certainly do it. It gives you a theory which has more. Well, in some sense, it doesn't have quite enough degrees of freedom to be the supergravity theory. Sorry, where was the question? Yeah, it doesn't have quite enough degrees of freedom to give you the supergravity theory we're interested in. Let me not say any more than that. Yeah. So what you actually want to do, so actually, we choose a smaller group. So we actually just choose the Lorentz group again. Inside this general linear group. And we can do that by just making, we do that by taking matrices of the form that look like, so here they look like the vector representation. Here we put 0, 0, and here we put the spinor representation. So what I mean, these are acting on this vector that looks, this thing that looks like this, on a vector. So on these indices, we just take the spinor representation, and on these indices, we take the vector representation. So we actually look at frames, so our frames, so put slightly better, our frames look like the following. So we have a here. It looks like E hat A. well, no, let me not write. E hat A, E hat alpha. And I should really say that, so E hat A prime is some R A B, E hat B, and E hat alpha prime is some rho alpha beta, E hat beta, where the rho looks like the exponential of a quarter some parameter theta mn gamma m gamma n, right? That's the spinor representation. Is that okay? So we're choosing a smaller group. And then you can go ahead, you can keep going. Oop. And you can introduce superconnections. So in the frame, we have some superconnection, which is going to look like some dm VA plus omega m AB, or let me call this big omega, VB. And this bit, right, this is like a dm and also a d mu, right? It takes derivatives along d by dxm and d by d theta mu. But I can introduce superconnections in the usual way, and we can have, again, we can have torsion and we can have curvature. Okay, I'll let you sleep a little bit. Yeah.
Does it not matter that the representation is not reducible?
That it's reducible like this? Yeah, no, that's okay. That's okay. Yep. Any other questions? Say again? Yeah, I'm sorry. This is a capital M for my coordinates, which are Z, M, capital X, little m, theta, mu. This is the coordinates for the super coordinates, so it's got both bosonic directions and fermionic directions. No, so these are like the coordinate basis, and this is like the frame basis. Yep. But again, you can work out torsion and curvature, and again, you might hope that what you want to do is now look at something which is a torsion-free spin 3-1 structure. But I'm afraid it's not even quite that. So if you want to do supergravity, yep. Can I define? Okay, so literally what it means is it's a supergroup which preserves, so 031 preserves a metric which looks like -1, 1, 1, 1. So O SP3 1 4, I can think of it as preserving some supermetric which looks like sorry, eta mn here, and then here I'm going to put, do you remember there was this C thing we defined, like psi bar with psi transpose times C? So here I'm going to put the thing which is C mu nu. It's got alpha indices. And this thing is antisymmetric. So you can think of it as the group that preserves this, or alternatively instead of C, or you could choose C to take the form if you want 1 minus 1 0, 0 1 minus 1 0 if you want. So it's got a bit that looks like an orthogonal bit, and it's got a bit that looks like a symplectic bit. So it's the supergroup that preserves that. Is that okay? Yeah. Okay, so can we take torsion free? And the answer is no, that's not quite what you want to do. So instead, one takes non-zero torsion. But the things that you take, the things are invariant under the spin 3-1 group. So let me tell you what I mean. So let's think about the torsion tensor. So the torsion tensor is going to be M, N, P. So it's going to have, and remember each thing, M, or let me write it as A, B, C. I'll do it in frame indices, A, B, C. And if you remember, each A index looks like an A index and an alpha index. So what do you take? So you take that almost all of these things vanish. So you take that T ABC is 0. You take that T A beta gamma is 0. You take that T alpha beta A is equal to T alpha A beta is 0. And then you take the T, here's the one you don't take to be 0, you take TA alpha beta to be the gamma matrix. And there's actually some other components here in principle, like I haven't written down things like A, B, alpha, and the rest are unconstrained. So it's like we're almost taking a torsion-free structure, but we have to turn on one bit of torsion here. And this bit of torsion, the gamma matrix is invariant under spin 3-1. It's got a rotation on the A index and it's got rotations on the alpha beta indices, and they cancel each other. That's the point of a gamma matrix, right? It's an intertwiner between the representations, so it's invariant. So this is an example of something where you take what's called singlet torsion. So the torsion doesn't vanish, but the torsion is always things which are singlets, things that are invariant under the group. Yeah.
One of the keys over there, I'm looking at the same, but the second one on the
This one? Oh, sorry, yeah, I wrote the wrong thing. What was I trying to write? Sorry, no, it's just all spinners, yeah, that's better. Yeah, thank you. That's better. Thank you. Any other questions? So this idea of singlet torsion happens in other geometries. So you might have heard of Sasaki-Einstein manifolds, or you might not have heard of Sasaki-Einstein manifolds. They're particular things that appear in, when you, If you have string compactifications where instead of compactifying to flat space, you want to compactify to ADS space, then the internal space is something that has some singlet torsion like this. So mathematicians have already looked at those things. So it's almost a kind of nice geometrical thing where you're setting some torsion-free connection, but not quite because of this. Let me just say briefly, how do you get the theory that we wrote down before? So there's some, you can gauge fix. That's choosing superdiffios. So with these superdiffeomorphisms you can make, you can gauge fix so that this frame, sorry, this is the dual frame. So the dual frame looks like the ordinary metric frame here in this component, 0 in this component, the gravitino in that component, and just a delta in that component, plus terms of order theta. So if you remember, I could always expand everything as a power series in the thetas. So this is the lowest component, the thing that's like got no thetas in it. Is that okay? So you can see that, and what happens is the higher ones get determined in terms of this. So you can see that we've got the degrees of freedom that we need. And interestingly, if you look at that torsion condition, if you work out this guy, you find that it basically looks like the Levi-Civita torsion, where it looks like if I have some conventional connection, so this is a spin 3-1 connection. When you work it out in this basis, you get a contribution from this guy, which is just the ordinary one. And then you get an extra contribution, which is actually twice K, A, B, C, where this is the thing that looks like psi bar gamma psi, right, that we wrote down in the supergravity action. And so setting this to 0 actually gives you a connection with torsion, which was the one we had. So that funny condition that we got a connection with torsion for an ordinary connection actually corresponded to torsion-free component in the super connection. So it's not so strange that you got something, it was somehow natural. So I'm just trying to give you a feel for where the things came from in the theory. Yes?
I guess the question is, why do you use these conditions?
Okay, so again, it's like, it's a little bit of magic, right? So people first just worked out what the theory was, and then they said, well, there must be a geometrical way of thinking about it. So let's, I mean, I'm misrepresenting the history, but, and tried to do it in superspace. This condition, even in flat space, you see that you need something like that. And that's precisely because you have Q bar looks like gamma M PM. So if you introduce a frame even in flat space, you need that term to get the super algebra. So in some sense, these conditions are modeling the conditions you have in just flat space. Okay. And I should also say that this formulation gives you, it gives you the off-shell theory. Yep. Yeah. No, what I mean is that this guy is a function of x and theta, and I can do a theta expansion of it, so it's got a leading term, which just depends on x. And then it's got a term that looks like mu, e mu m a x. And then it's got a term like theta squared and theta cubed to the fourth. So I just mean that term is that. Yeah, so it's just that if there were no bosonic, then you'd just have this as your frame. This mixes in a bit of the fermionic directions into your frame. Yeah. So for the fermionic directions, it's just a sort of delta basis. That's what this is. You can always choose a gauge where this is just constant. Yeah. Yeah.
Is there a notion of small theta, big theta?
No. So because it's fermionic, you just, if you like, the convergence question isn't a question. It's just a finite power series. Yeah, so you don't have to think about large and small. Yeah. Yeah.
So this single portion, can this be derived using the first order formalism, or is this just an input that you're putting into your theory to obtain supergravity?
This guy?
This single portion. So if you did the first order formalism,
Yep.
then you get a portion out of that.
Yes. No, you have to put, because yeah, you could try and do that if you coupled to some extra fields, then you would do that formalism and you'd get some torsion maybe from some extra fermionic fields or something. But it's like we're doing pure gravity here, so it's like doing that formalism for pure Einstein theory, and then you don't get any torsion in the omega equation. Yeah, good question. Are there any other questions? All right. Just wanted to say that this gives you the off-shell theory. So it actually has auxiliary fields. So it really has some extra degrees of freedom in addition to these ones. And so you can actually use it to consider corrections to the two derivative theory. So all I'm saying is, if you remember before, I said one shell, to the algebra, we have to use the equations of motion. Here, we don't have to do that. I have some extra fields around, which I haven't told you about, which means that the algebra just closes. So now I could think about writing down more general actions in terms of the curvature. So again, here, the action, so this two derivative action, this is built from the supercurvature of this connection, right? So there's an analog of the Levi-Civita connection that satisfies those torsion conditions, and then I can build some curvature from it, and the action that we wrote down before is basically that curvature in a somewhat complicated way, but okay. So if you're relatively happy, I'm going to change topic, and I'm now going to talk about 11-dimensional supergravity. Yeah. Okay, that's actually a really interesting question. So there is a way of doing this with zero torsion, and you look at a slightly different group. So you look at a group that looks like SO31, spin 31, and I set these guys to 0. you can allow this to have something here. So that's some funny, it's not a simple group. And actually, you can think then as having zero torsion. So you can actually do that group and introduce a connection with zero torsion, and that will give you the same theory once you suitably gauge fix. So that's the best I know that's a honestly zero torsion theory. Yep. Any other questions? Okay, so let's so there's we could have had a whole course just on doing superspace and supergravity and superspace, right? And how that works, and you have to work through a whole load of Bianchi identities and understand how the torsion constrains the curvature, and there's all sorts of beautiful stuff there. There are supergravity theories in all dimensions up to 11. So I could also have given a course where I just tell you about each supergravity theory in each dimension. I've told you about the one in 4 dimensions. I'll tell you about the one in 11 dimensions, and then we'll see most of the ingredients that come into the other theories by looking at those 2. Okay? And then depending where we are, I'll give you a little summary of the other theories, or I'll focus more on supersymmetric backgrounds. Does that sound okay? All right, so let's, so I'm afraid we're going to have even more indices. So let's do, so we're going to do n equal 1, d equals 11 supergravity. And so this is the maximal dimension in which supergravity exists. And that's because in higher dimensions, there's not a multiplet that has only up to spin 2. You'll always have something above spin 2 in the supermultiplet. So the gravity multiplet, so let me just remember that we have Cliff 10.1, looks like M32R plus M32R. So our spinners are going to be 32 component and Majorana. And the gravity multiplet has a spin 2 field, a spin 3/2 field, and it has another field in it, which is totally, so this is like spin 2, this is spin 3/2. This is a 3 form. Just means it's totally anti-symmetric in M, N, P. So unlike the 4-dimensional case, we have more bosonic fields. Just doing the analysis of the representations of super Poincare, you find that the representation now has another field in it. So we want some, so we want a nonlinear gravity theory. So let me just tell you what it is. And then we will do some unpacking. So here's the action. So we have again a gravitational coupling. We're now doing integral over 11-dimensional space. We have the measure. We have a curvature for some connection nabla. I'm going to have 3 different connections, and I'm going to tell you what they each are. Then we have the usual Gravitino term. So this is like the usual Einstein term, but for some connection actually with torsion. Then we get this D operator like before, and this is connected to a connection I'll call nabla prime. Then we get what is really a kinetic term for this three-form field, so I'll explain. So I'm going to have to tell you what a lot of these things are. Okay, then there's a term that looks like, in the usual conventions, root 3 over 192. Don't ask me why. Psi n, and then I have gamma A, B, C, D. I'm not sure why I wrote it this way, but anyway, NP. So this is 1, 2, 3, 4, 5, 6 gamma matrices, anti-symmetrized. Yeah.
Sorry, I think you said root 3.
Oh, I do that.
Which one is it?
It's root 2. Yep. Yep. I'm a theoretical physicist. Is that what I'm supposed to be? I do this. Have I done this yet? I write this, and then someone asks a question, and I keep my hand held. No, okay, right. Okay, 12 gamma AB gamma G. That's the metric. G. Well, I don't know whether I'm in. Let me write E and EF. Let me do everything in frame indices. So I have eta CE, eta DF, and then I have psi F, and then I have F A B C D plus another F, I'll call it F hat A B C D. And then, yeah. Yes, no wonder you're worrying. Okay. Is that better? Okay. And then we have another term which is 2 root 2, and I promise it's root 2, over 144 squared. And then an epsilon tensor, that's just something totally antisymmetric and, right, like in 11 indices, F, M1, M2, M3, M4, F, M5, M6, M7, M8, A, M9, M10, M11. And then I close the bracket. Okay. So this is the way to write the action. If you remember before, by introducing these connections with torsion, we could write the action in the most compact way that didn't have 4 Fermi terms in it. So this is the same idea. So I've got some connections here with torsion. I've got 2 of them. So let's explain a little bit what everything is. So first of all, I have this F, M, N, P, Q. This is 4 times the derivative M, A, N, P, Q. Or equivalently, this is dA, M, N, P, Q, if you're used to thinking about differential forms. This is like the field strength for a 3-form potential. So you should compare this with electromagnetism, right, which is a field strength for a 2-form potential. So you've probably seen these things before-ish. So this theory has something in it which is like the analog of electromagnetism, but now with more indices. Then I had this F hat thing. This is F with some terms that depend on the fermions. So 3/2, 1 on root 2, psi bar m, gamma np, psi q. This is sometimes called the supercovariant form. What that means is that when you do the supersymmetry transformations, it doesn't have any derivatives of the superparameter in it, but it is what it is. Then I've got, so I've told you what these two things are. I've got to tell you what these two connections are. So the regular connection is Levi-Civita plus a term which we'll call KMAB. And here we have KMAB. Looks like minus a quarter psi bar m gamma b psi a minus psi bar a gamma m psi b plus psi bar b gamma a psi m plus 1/8 psi bar n gamma np mab psi p. Okay, this bit is exactly what we had in 4 dimensions, the second expression. This bit would vanish in 4 dimensions because it's a gamma matrix anti-symmetrized over 5 things. So this is actually, this bit's universal. This kind of connection to all supergravities. So this kind of torsion bit actually appears in all supergravities. Then we have yep. When I write this, because I got AB here and I don't have anything there. Okay, so what I really mean is that nabla M on VA is nabla Levi-Civita M on VA plus K M AB VB. Yeah, I'm getting lazy. Yeah.
Is there an example of a solution to this action?
Flat space. With the fermionic part turned on? Yeah, so there are. I mean, it depends how complicated you want to get. So again, I can do simple things, like I can do a wave of gravitinos in flat space. That would also have a solution to this. Is that true? If I choose the polarizations correctly. If you want more complicated things, it's your problem to find solutions to some non-trivial partial differential equations. So, yeah.
But the original solutions will always be there. Radius, squash radius.
So anything where I turn off the fermions will still be a solution. Yeah, there's nothing. The bosons will not source the fermions. So, yeah. Any other questions? Yeah. Is A the potential?
Is this associated with a gauge?
Yeah, so you should think of this as like a gauge symmetry. To a mathematician, it's something called, but it's not because it's only got, yes, so let me say that. So we have a gauge symmetry, which is A, M, and P goes to A, M, and P plus 3 times the derivative of something. Because I put that in the field strength, then F, M, N, P, Q just goes to F, M, N, P, Q. Doesn't change because the two derivatives will cancel because it's anti-symmetrized. That's exactly like, so you should compare F equals dA and delta A equals d lambda. That's what we're saying in form language. And this could be a 1 form and a 2 form, or a 3 form and a 4 form. If it was a 1 form and a 2 form, that would be like electromagnetism. If it's a 3 form and a 4 form, it's what this is. Now, you know in electromagnetism, you can think of it as a U-1 gauge. And in electromagnetism, this would be a scalar, and it's telling you about the U-1 gauge symmetry. Here, it's not a scalar, it's a 2 form. So how do I think about that? So there's a question whether you can take the notion of gauge symmetries and gauge bundles, U1 bundles, and promote them to something for 2 forms or 3 forms or 4 forms. So there is a way of doing that, and it's what's called a, okay. The French, anyone who speaks French can pronounce it the correct way, gerbe, right? So, or a gerbe, if I'm a... that's a kind of generalization of U1 gauge theory to higher objects. And there's a really interesting thing, which is U1 gauge theory. We know how to do U1, but we also know how to do non-abelian things. We know how to do this story for the abelian ones. We do not know how to do this story for non-abelian things. There isn't a sort of natural extension. Yep. Excellent. So it is, and this is called the Chern-Simons term. And it's invariant because I'm doing an integral. So when I do this, I get a total derivative, and the integral vanishes. Yeah. Well, then you have to do something to make sure it's a Chern-Simons term. You need to think about what you're doing on the boundaries. But yeah, yeah, yeah.
I guess like this gauge theory story, people talk about like extended operators. And you have like a line operator. There's like instead of one form, you have 2 forms.
If you're doing generalized symmetries or something, yep.
Is there like an extended objects that you should be thinking of this?
There absolutely is. So like, and you kind of know what it's going to be. So you know that M theory, this is the low energy theory of M theory, has in it membranes and 5 branes. So this 3-form potential naturally couples to a membrane. In the same way that a 1-form potential couples to a particle carries charge, U1 charge. If you have some charge for this 4 form, it's going to be an extended object, which is a membrane. So this couples to a membrane. And the supergravity theory has solutions in it which look like the gravitational and A field around like a flat membrane. Like, so I can just, in the same way I can have a Schwarzschild solution that looks like the gravitational field around a point mass. These things have solutions called the flat membrane solutions that look like the gravitational fields around a membrane. Yeah. Yeah, so the way I'm doing it, this is, well, I've got a square root of g there, so no, it's actually a tensor. If I put the square root of g outside, so this is honestly like a tensor with 11 indices. If I'd absorb the square root of g into it, then it would be a number. Yeah, yeah, yeah. Well, if there's any supersymmetric theory in 11 dimensions, this is the only theory with two derivatives I can write down that's supersymmetric. So any supersymmetric theory in 11 dimensions has to have this as its low energy description. Right? So this theory is unique. This is the only supergravity theory with two, this is the only supersymmetric theory with two derivatives I can write down in 11 dimensions. And it has to have gravity in it because that's the, yeah. That was my cop-out answer. Yeah.
What about the D-4 theory we wrote down earlier? What is the low energy theory?
What are they the low energy theory of? So this is okay. Let's do it. So there's an interesting question, which is that these are all classical theories. So they're not sensible as UV complete quantum theories, as you've been learning in CFT, right? You need to think about some UV completion. So there's a sort of game, which is like I write down every gravitational theory I can think of in low dimensions. And then we ask, which of them actually have a UV completion? Which of them actually come from some sensible upstairs theory that's actually a sensible UV theory? So if you're a string theorist, you say, well, I know that any that come from string theory will have a nice UV completion. So if I can find a string theory that in the low energy limit looks like my n equal 1, d equals 4 theory, then I can kind of argue that, well, in a sense, it exists because it's a low energy theory of string theory. So that you can do. You can put string theory on, for example, a Calabi-Yau background. You took the heterotic string on a Calabi-Yau background. It will give you something. Part of the theory will be the n equal 1 four-dimensional theory I wrote down. There's this question that goes under the words of landscape and swampland, which is like, which, if we work the other way around and you just start writing down lots of theories in 4 dimensions, which of them actually come from, or in the landscape, come from sensible UV completions and which ones don't? And there the game is, it's pretty clear that not all theories come from UV completions. So the question is, what are the characteristics of those theories so that they do? And then you have to be very clever and come up with some sensible conjecture about which ones do and which ones don't. Of course, you come up with any conjecture you want, right? But you have to come up with something that makes sense. But I think in some sense, if you were a sort of all in with string theory, I think what you would say is that the existence of these supergravity theories is kind of because there's this string theory hanging around in the background. But that's a bit of a prejudice view. Yeah. No, so the moment you go to n equal 2, you'll have more than spin 2 in your multiplet. Yep. All right, so let me just write down the other connection, and then we'll take, since you're asking me lots of questions, we'll then take a short break, and then we'll keep going. All right, so this was the connection that appeared in this term. So this is the curvature for that, this is the Ricci scalar for that connection with torsion. And then there's another connection, which I called nabla prime, which is Levi-Civita. And it has the same term, it has the same, so this is plus some k prime, MAB, and k prime, MAB, has the same minus a quarter term. That's the same as above. And then instead of having an 8th here, it has a 16th. And then just to complicate matters further, there's this D operator here, and D nabla prime M of psi n is just, as before, we only take the spinor bit. So in general, there should have been a connection that also saw the vector index, but we dropped that term, just as we did in the four-dimensional case. If this connection had no torsion, that term wouldn't contribute because it's anti-symmetrized. But this connection does have torsion, so it's actually, that's not what we're doing. We're doing something else. Okay? Okay. So that's all the ingredients. Let's take let's come back at 10 past, and I'll tell you a bit more about this theory and what the supersymmetry transformations are. Okay. So I wrote down the supersymmetry action for you. Just to stress again, this is the only two-derivative supersymmetric theory you can write down in 11 dimensions. There is no other theory. It has to have this matter in it. It has to take this form with two derivatives. So you might think it's sort of special in some way. And I told you various bits that go into this. We also need the supersymmetry transformations. So let me just tell you what they are. So again, we have a variation of the bosonic frame, and that just takes the same form it did in 4 dimensions. Again, that's a sort of universal thing. The variation of the spinor, of the gravitino, has another connection, different from both of those two. And then it has a term which includes the full form. And then here it's this supercovariant thing again, the f hat acting on epsilon. And then there's the variation of the 3 form itself. And again, that's going to depend on the gravitino. And yeah. Oh, so you can have free theories, but once you put any interactions, then you're stuck with this. So the only multiplet, the smallest multiplet, has spin 2 in it. Yep. Right? So those are the supersymmetry transformations, and again, you go ahead and you calculate, or you don't. And what's this connection? Oh, this is the Levi-Civita one minus, and it only has the quarter term. So Sorry, let me write it slightly more precisely. So plus k double prime m a b, and this k double prime m a b is just this term. So we get three different connections that appear. Each of them share the first term, but they have an eighth, a 16th, and none of the term with a 5 gamma matrix in it. So again, there's just all these different connections. Yep. Oh, yeah, that should be an M. Thank you. Yeah, let me make my life easier. Thank you. Yep. Oh, did I? I would trust them, not me. But let's. I think I might have changed the order of the indices from what they had. So did they have? They may. Yep. Okay, and again, so some of these different connections you can see as appearing when you do the corresponding superspace calculation, right? It's in the way I did before. But again, there's some very delicate thing going on between having these different connections with torsion and the way their supersymmetry cancels. Also, in some sense, by using these different connections, we write it in the simplest form. We kind of get rid of all the terms that would look like 4 fermions. So I could have written everything in terms of Levi-Civita connection, and then I'd have a whole load of 4 fermion terms coming out. It again closes on shell. Excellent question. So let me tell you how it works. So the closure of the algebra is slightly more complicated. So for the SUSY algebra, what are the symmetries we have? We have supersymmetry, we have diffeomorphisms, which is like, xm goes to xm minus psi m of x. We have local Lorentz, which is some rotation of the frame. Let me write it this way. I can just write that. And then we also now have local gauge. Also gauge, it's the gauge symmetry of the 3 form, right? Which is that A MNP goes to A MNP plus some d lambda anti-symmetrized. So if you remember before, what we found was that when we did the anti-commutator of 2 supersymmetries, it generated a diffeomorphism, but it also generated each of these other things. It also generated local Lorentz and SUSY. And what's going to happen now, it's also going to generate a local gauge. So if we do the anti-commutator of 2 supersymmetry transformations, we find that it looks like the combination of a diffeomorphism, of a local Lorentz, of a gauge transformation, and a local supersymmetry. And again, this is all, it closes on shell. So again, you need the equations of motion. And what are the parameters, just so you have them? So the diffeomorphism is given by a half epsilon bar 2 gamma m epsilon 1. That was as before. The Lorentz transformation has two bits. So it has a bit that we had before, which depends on the spin connection, and that's the spin connection for this guy. And then it has a bit that depends on the F's. Square root of 2. I'm sorry, there's so many indices here. Gamma A, B, C, D, E, F. And then I get the hatted guy, C, D, E, F. And then I get another term with 24 gamma C, D, F hat A, B, C, D, epsilon 2. I get a gauge transformation that again depends on the field A and has an extra piece and finally I get a supersymmetry transformation that depends, again, is field dependent. Okay, so it's quite complicated. This guy? So that's the spin connection, and it's the double prime one. Yep. And here you yep. Sorry, we're yep. Oh, sorry, that's 2p. Yes. Yep. Yep. Any other? Okay, so you might ask, what about, well, while I'm at it, let's just go back to this Chern-Simons term. So for F, if we just look at the action for F, it looks something like 1 on 2 kappa squared. And then we can write it in the following way. We have the square root of minus g minus, what is it, 1 on 24 FMMPQ, FMMPQ. And then this last term, if you write it in form language, you can write as minus root 2 on 6 kappa squared, and then it's the integral of f wedge A, which is 4 plus 4 plus 3, that's 11. So it's something you can integrate over the manifold if you know about differential forms. If you don't know about differential forms, this is going to be very obscure. But and the point is that the equations of motion here are going to look something like nabla m f m n p q, and up to a factor, some number, which I didn't work out. This is going to look like epsilon n p q r1 through r8, f r1, r2, r3, r4, f r5, r6, r7, r8. So you get a contribution from here, which is like that would be just like electromagnetism, but with more indices. But you also get this contribution from this Chern-Simons term. So there's an interesting self-interaction of the four form. And that characteristic of supergravity theories in higher dimension than 4. You often start seeing more form fields, and you start seeing things like the Chern-Simons term appearing. In fact, they can be quite complicated, Chern-Simons terms. Yeah.
If I remember correctly, the Chern-Simons term appears also in gravity 2+1 dimension.
It can, yep.
What is so special about the dimension where this term appears?
About 3 and
2+1 or 11?
excellent. So you want, if it's a pure Chern-Simon, A, wedge D, wedge local. So you take forms of different degree. So if the form has degree P, this would be like P plus 1. So this would be like 3P plus 2. So you can write down this term, which is just FFA. When the form has of degree P, the dimension will have to be 3P plus 2, I hope. So does that work? So this was supposed to be 3. This was 3 times 3 plus 2 is 11. So we can write, so when P is 3, we have D equals 11. When P is 2, I guess we have D equals 5, right? Then you can also sometimes write down terms which look like just F wedge A. And then you'll get like 2P plus 1. So then if P is 1, you can do it in 3 dimensions and so on, right? So depending on how many F's you have in the Chern-Simons term, you can write it. Different Chern-Simons terms in different dimensions. So no dimension, it's not possible to write any term. I think it's always going to be, I can't do it, but I think it's going to always be odd dimensional, right? I can't do that. Someone, you can think about that better than I can. Yeah. Yeah. Yes. So in the supergravity, a priori, there's nothing about F that's quantized. Just some field. It's a bit like when you do electromagnetism, you secretly know that electromagnetism is for a U1 gauge field. And there are some things that carry U1 charge. But if you just wrote down the kinetic term for electromagnetism, that could strictly be for a U1 gauge theory or for an R gauge theory, where you can make, the gauge transformation doesn't come back to itself after you go to 2 pi. It's just you can do arbitrary gauge transformations. And so if it's that theory, there's no quantization because there's no 2 pi integer thing going on, right? So the thing that appears in supergravity is a bit like this one a priori. You don't have anything that's charged with respect to it, so you don't have any quantization. Once you start having objects that carry charge for it, then you can ask, is it more like that or more like that? And then when we have the M2 branes and the M5 branes, we can say, actually, it's more like that. And this flux actually comes in units, comes in quantized units. And then, yes, there's a complication then about, so you have electric and magnetic charge, depending whether it's the membrane or the 5 brane. And because of this term here, the electric and magnetic charges are not quite as simple as you might think they were. Yep. Okay. All right, so let's see. So you might ask here about superspace. What if we did the same thing that we did in the 4-dimensional case? And so now we've got some manifold which is going to have coordinates Zm, which are xm, theta mu, and now this is running from 1 to 32, right? And the frame, so if I look at frames on this space, the frame bundle is going to be a GL1132 principal bundle. So frames are going to be related by this complicated general linear thing. And again, I can look at a structure which is a spin 10(1) inside GL1132, just as I did in the other case. And there's going to be torsion constraints. And again, the key one is going to be there's a torsion component, which again I set equal to the gamma matrix. And there's going to be a bunch of other ones. So I'm not writing them down, but there's going to be other things that I set to 0. So it's very like the other case, but in this case, you find that the torsion constraints imply the equations of motion. So this superspace is on shell. So this was a couple of people asked, this is like, this is the difficulty of doing superspace in higher dimensional where you have more fermionic directions. In general, we don't know how to write down torsion constraints that give you the theory off, so that you can write nice off-shell theories. You can on-shell, but that's going to be hard to think about corrections to the theory. Okay, but you can do the same story again. Yeah. This is the only, there's no matter multiplet. So the smallest multiplet you can write has spin 2 in it, 11 dimensions. So you've got no freedom to add anything else to the theory. Yeah. Any other questions? Yeah. Say again. No, so if you remember in 4D, we saw that we had chiral multiplets and vector multiplets and the gravity multiplets. So there were several things we could do there. So if indeed we did that thing of compactifying, you would get the gravity multiplet, but you'd also get some matter. And that's the whole game, right? So if you want to do the standard model in string theory, you want to take a 10-dimensional theory, compactify it, and see if the matter you get downstairs is the stuff that fits in the standard model. It can't contain matter as itself, but when you compactify them, go to a smaller amount of supersymmetry, some of these fields can start looking like matter in 4 dimensions. So the history was, okay, I'll tell you something else. This theory, when you do it a naive compactification, you can't get chiral matter. If you get one chirality of matter, you'll always get the other chirality. So how might you get a fermion out of this? So in a really simple way, you've got this thing, you've got this gravitino, right? If now my index splits, so I've got a mu index and I need another letter. I'll call it mu and alpha hat. And mu is 0, 1, 2, 3, and alpha hat is 4 up to 10. If I want to get something that looks like it just spin half with respect to this space, well, I could take the alpha hat component here, because that's going to look like a vector in the internal space, but from the external space, it looks like a scalar. So this would give me something that was spin 1/2. So that's a candidate for the electron. But what happens is, in this theory, you can show, Witten showed actually, famously made an argument at a conference in Shelter Island, that however you compactify, you're always going to get as many fields of one chirality as the other. It's always going to be symmetric between the two chiralities. And we know the standard model is not symmetric. So the history was people wrote down this theory, and it's so beautiful. The idea was like, oh, if you find the right compactification, that's going to give us the standard model. That was why originally 11-dimensional supergravity was so exciting. And then it was pointed out that no, that doesn't work because it can't give you a chiral theory. Looks like it's. But then actually it came back again, because what you can do is you can choose compactifications that kind of have an extra chiral symmetry built into them. So that's going to sound very strange. So what I mean is, there's something called Hajava-Witten theory. So you do the following thing. This is like a brain world theory. So you take your space-time to be a block where this is 10 dimensions, and this is the 11th dimension. And it's just got two ends. And you're now allowed to put extra matter at the ends of these, at the ends of the world. And you have to put just the right matter in so that the theory is quantum consistent, doesn't have any quantum anomalies. This matter can be chiral. So now when you do a dimensional reduction of that, you can get something that's a chiral theory. And in the duality, this theory is dual to the heterotic theory. This is dual to heterotic. So the heterotic theory is a famous 10-dimensional theory, string theory, which is chiral. So originally, people dropped 11-dimensional supergravity, and they said, oh, but then they discovered heterotic theory that's chiral. So now we want to do dimensional reduction of chiral. That chiral theory, that's going to give us. And so there's a whole industry of looking at compactifications of the heterotic string that give you the standard model. And you can get three families of matter. You can get the Higgs field. You can get like, you can suppress like proton decay, which comes from grand unified theories. People are even beginning to calculate Yukawa couplings, right? So there are examples where you can basically get it out of the heterotic theory. But 11-dimensional supergravity came back when Hajava and Witten realized that the heterotic theory is dual to this 11-dimensional theory with these ends of the worlds. And that was when everyone started doing brain world models of 20 years ago, more. Okay, you sucked me into telling you about something else. Are there other questions? Yeah.
Are there any solutions that include like simple solutions that include quadratic fields?
That include?
Like solutions with supersymmetry in this case. Simple solutions.
Yes. So there's a very simple solution, which is the solution around a membrane, which is supersymmetric. So there's a solution. Well, yeah. All right. So right, so I've told you about two of these supergravity theories. As I said, there's a whole lot of other supergravity theories in other dimensions with different amounts of supersymmetry. The next thing I was going to tell you was to go back to the four-dimensional theory and ask how you can couple it to matter, because that's actually the kind of phenomenological theories that people look at. And we're then going to have to talk about, again, we're going to do some more geometry because we'll have some scalar fields around, and we'll. To tell you that whole story is quite a long story. So I'm tempted to tell you a little bit about it, and then I might not give you every detail, and then I'll try and tell you a bit about supersymmetric backgrounds. So does that sound like a good way to go in the next couple of lectures? Okay, so let me just run a little bit over, and I'll start telling you a little bit about the four-dimensional theory coupled to matter. This is kind of characteristic. This has properties that are characteristic of all supergravity theories. So that's why I wanted to tell you about it. So let's do general D equals 4 n equals 1 supergravity coupled to matter. Okay, so what were the matter multiplets? So I told you what these were before. So we had this chiral multiplet, which had a complex scalar field that was spin 0, and a fermion chi, which was spin 1/2. And we had the vector multiplet, which had a gauge field, which was spin 1, and a spin 1/2 field. And then we had the gravity multiplet, which was HMN and psi m. So this was spin 2, and this was spin 3/2. There are some other multiplets you sometimes see called tensor multiplets and so on. I'm not going to put them all in, but you can do it. They're in some sense dual to some of these other multiplets, but let's just focus on this because this basically can tell you, pretty much tells you everything. So what we want is to do, let's just focus. So what we want to do is let me write down the action, and we'll focus on the chiral field geometry. So I'm not going to tell you the full action. So let's just do the bosonic action. And the idea is we're now going to have multiple fields. So we're going to have some Z, and I'll call them I, and I guess I could have the complex conjugates. So these are chiral fields, multiple chiral fields, and I'm going to have gauge fields. So I'm going to have some A, M, A. So I've got a capital index, sorry about the two A's. There's a capital index on here, which is labeling. So these are some number of chiral fields, and I'm going to have some number of gauge fields. And as you might hope, these gauge fields will have some gauge group. It might be some non-abelian gauge group. So I want to write down the most general, we want the most general supersymmetric action coupled to gravity. Okay? So I told you before how to do it just for the gravity multiplet. Now I'm going to do it for the gravity multiplet plus these other two multiplets. And what's going to happen, let me tell you what's going to happen. We're going to think of these fields as like coordinates on some other space. So these fields are going to look like, these things are going to turn into coordinates on and it turns out Kähler, and it's actually something called Kähler-Hodge space, field space, which I'll try and call X to distinguish it from the manifold. So this is not a space-time manifold, it's a different manifold, which is where the fields live. But it also has its own metric and curvature and so on. And that turns out that supersymmetry tells you that this has to be a Kähler manifold. It actually has to be something slightly stronger called a Kähler-Hodge manifold. Okay? And then the way that the gauge fields appear is that this Kähler manifold, so these comes from isometries of X. So you've got this space, which is going to be some curved space where the fields lived, but that space may have some isometries, right? You may have some symmetries. If it's got some symmetries, then you can have gauge fields for those symmetry directions. So those are the ingredients that are going to go into the full action. So maybe I'll stop there, and then this afternoon I'll tell you what the action looks like and how those geometrical ingredients appear. Yeah. So it's coming from the fact that supersymmetry is forcing it on you. So the fact you want a supersymmetric theory, we already saw that the chiral multiplets have to be complex things. So they already have to have some complex structure hanging around because they have to be complex fields. So, and then if you keep turning the crank and seeing like what supersymmetry tells you, it tells you more and more structure on here and tells you actually has to be Kähler. So it's sort of all the time, you write down a theory, a priori it could have all sorts of interaction terms, but supersymmetry restricts the form of those interaction terms, and that's what's going on. Oh, I see what you mean. It's just distance. I don't know what to say other than distance in field space. Yeah. Yeah.
Why without considering the one of the odds?
Good. We could. When you do that, it forces you to have more supersymmetries. So if you couple it to that, the only way to do it is to have n equal 2. Yeah.
So I have a question about the dimension one.
Yep.
BPS solutions known in this action?
Yes, there's lots of BPS solutions known.
Is there an ideation method construction?
No, because it's gravitational, right? So ADHM is nice for kind of gauge fields. No, it's a more kind of ad hoc thing. We have ways of constructing them. They're typically, you can always think of them, this is a subject dear to my heart, you can always think of them as coming from being sourced by branes one way or another. So there's a sort of story by which you can think of them as either single branes or intersecting branes or, yeah. Any other questions? All right, I will see you.